Good evening, friends from ASEAN subcontinent, and good morning to colleagues from US, like our speaker, Professor Supriyo Datta, and good afternoon to friends from Europe. So wherever you are, I'm very happy that you have managed to join this seminar. I think the seminar is going very well, and all credit goes to speakers like Professor Datta, who have been very kind and supportive, agreeing, giving these talks, and the audience, wonderful audience like you all, who have been very generous in joining all the seminars recently and interacting with the speakers and really vibrant discussions. I think today's speaker, Professor Datta, does not actually need any formal introduction, but I just give a little bit introduction for the benefit of some young students who may not know him. Otherwise, he is very well known name. So Professor Datta is Indian origin. He actually received his BTech from IIT Kharagpur, I think 1975, and he got the President of India gold medal for his BTech. Then he moved to University of Illinois in Urbana-Champaign for his MS and PhD degrees, where he got in 1977, 1979 for the PhD. And since 1981, he is working at Purdue University, where he is currently working as a Thomas Duncan Distinguished Professor since 1999 in the School of Electrical Engineering. He has a wonderful career. I mean, very quickly, I will read a few things. He started his career in the field of ultrasonics and was selected by the ultrasonics group as its outstanding young engineer to receive an IEEE Centennial Key to the Future Award, and by the ASEE to receive the Dorman Award for his book on surface acoustic wave devices. He has worked on many things. He was elected as a member into the National Academy of Engineering in 2012 for quantum transport modeling in nanoscale electronic devices. In 1990, he proposed the use of spin-orbit coupling to control electron spin with an electric field rather than a magnetic field. This was experimentally demonstrated in 1997 and is widely used in the field of spintronics. This proposal planted the idea that spin could be used in its own right as a means to carry and manipulate information, and very important for the field of spintronics. In 2008, along with Saif Salahuddin, he proposed the concept of negative capacitance devices, which is now considered a prime candidate for reducing dissipation and extending Moore's law. He has got numerous awards. Just to tell a few, in 2011, he received the William Proctor Prize for Scientific Achievement, William Proctor Prize for Scientific Achievement in 2011. He is a fellow of the American Physical Society as well as the Institute of Electrical and Electronics Engineering, that is IEEE, and has received 2 IEEE Technical Field Awards, the 2002 IEEE Ledo Brunetti Award and the 2008 IEEE Leon K. Kitzmeier Graduate Teaching Award. He is included in Purdue's Book of Great Teachers and won the Herbert Newby McCoy Award. And if you look Wikipedia, it says, which we all agree, and we know that he has been called as one of the most original thinkers in the field of nanoscale electronics. He has written many books, and we are really privileged and very happy to welcome you, Professor Datta. And we are really looking forward to a lecture. There are many participants. I think all are looking forward to a lecture. I just like to mention that during the lecture, we don't take any questions. So if you have any question, kindly write in your chat box or just raise your hand. After the lecture, we will take the questions and we can have really nice interactions. And at the end of the lecture, I will request all of you to switch on your camera to take a group photo, screenshot, and then we will take the question answer and finally we'll end. So with this note, thank you again so much, Professor Datta, and we are looking forward to a lecture. Thank you.
Thank you very much for the very kind introduction. And so you can hear me clearly, right? And you can see the screen?
Yes, yes.
Okay. Okay. And you can see my laser pointer here, right? Okay.
Yes.
Good, good. Okay. Thank you again. And yeah, it's a privilege, and thank you all for coming. And before I start, let me just acknowledge the people whose work I'll be talking about. I mean, this is something we've been working on for the last 5 to 10 years, I guess. And so there's many people who have contributed over the years, and some of them are still at Purdue working with me, like the top 4, and others have moved on and they're working in different places. And we are still collaborating on many aspects. So I just wanted to acknowledge everyone before I start. Okay, so what I'd like to talk about is this concept of a p-bit, as something intermediate between a bit and a qubit. And in the context of spintronics, as you know, one place where you see this concept of spin is in the field of quantum computing, where a basic qubit is often viewed as a 2-level spin system. Okay? That's what you might call a single spin. Now, at the other end, you have this digital computing, which is everywhere, like what's in your laptops and all. And there you have a bit, which can be 0 or 1, and they're stored in, of course, there are different ways of storing it, but one way is in the form of a stable magnet that can point in one direction or the opposite direction. And in MRAM technology, I guess that's what is used to store bits. So now what we call this p bits is something in between. So that's what you might call this unstable magnet. So in fact, one of the problems people deal with in the context of digital computing is that as you make these magnets smaller in MRAM technology, they tend to become unstable. So that's usually called a problem. And people have been working very hard in terms of how to make them stable, even when you make them small. And what we have been arguing is that these bad magnets, the ones that you really don't want for this memory technology, those could be used for a different kind of computing, this probabilistic computing, right? And that's what we call a p-bit. Okay. Now, let me tell you a little bit about this distinction between digital computing and probabilistic computing. So what we have felt is this probabilistic computing conceptually, it's classical. So in that sense has a lot of overlap with digital computing. But on the other hand, it brings in certain features of quantum computing. And so this is a popular article we recently wrote earlier this year, which you could look up to see where we talk about this connection between probabilistic and quantum computing. Now, in digital circuits, as I mentioned, you store information in the form of bits. So you have zeros and ones. And if you have the small n number of bits, you'll represent information as 1, 0, 0, 1, etc. And the way you process information is you use gates to turn them into another set and so on. So that's how you process information. At any point in time, if you ask, well, what is the state of the system? You give these n numbers, n binary things, 1, 1, 0, 0, etc. Now, in a probabilistic circuit, on the other hand, it's like, well, it's neither 0 nor 1, but has a certain probability of being 0 or 1. Right? And as it evolves then, in order to describe the state of the system, you have to specify this probability function, the PDF or probability distribution function. So you have to give this number, the probability number for each of the configurations. And how many configurations are there? Well, if there's small n bits, then there are 2 to the power n configurations, because each bit can be 0 or 1. And so you have a probability distribution function with 2 to the power n components. Okay. Now, in time then, what happens is that this distribution function evolves. And this evolution you could describe in terms of a matrix, the stochastic matrix, whose dimensions is 2 to the power n by 2 to the power n. Now, one point I want to stress is this relation between n and 2 to the power n, that as n increases, this 2 to the power n increases very fast, exponentially, essentially. So if you have 10 bits, then the number of configurations is about 1,000. 20 bits, it's 1,000,000. 40 bits, it's like 1,000,000,000,000. So it goes up very fast. And a lot of the power of probabilistic or quantum computing really comes from this, that we are operating in this n space. We are working with n bits, but underlying it is this 2 to the power n space, this enormous space with lots of possibilities. And that's where really the power of all this comes. And in that sense, probabilistic computing has a similarity to quantum computing. I mean, the basic difference being in probabilistic computing, you have a probability distribution function, whereas in quantum computing, you have a wave function, which is a complex number. And that complex number, when you square it, you get the probability. But this basic thing that they both kind of operate in the 2 to the power n space, in the sense the probability distribution function has 2 to the power n components. The wave function also has this 2 to the power n components. And the power of quantum computing comes from that fact that 2 to the power n is a huge number for for small n's. I mean, just n being 40 already gives you like 1,000,000,000,000 possibilities. But the important difference, of course, is that in probabilistic computing, you're dealing with a positive number. Probabilities are all positive, whereas in the quantum case, it's complex. Now, in practice, how do you do any practical calculation? Because as I mentioned, 2 to the power n is a huge number. And the method that is widely used, an enormous field in itself, is this idea of sampling, that you don't actually go through this full space, but rather in a clever way, you sample some of this and try to get reliable answers. And the key element there is this random number generators, because there is what I call this Monte Carlo sampling methods. That's what is widely used for these problems. Now, could you use these sampling methods for quantum computing? Well, yes, but with certain caveats. So that's this field that you refer to as quantum Monte Carlo. So you can do quantum problems also, but not quite as efficiently as you can do the classical problems. So I'll try to give you a little bit of a flavor of that towards the end of the talk. We'll come back to it, come back to this point. Now, usually what happens is, as I said, the sampling methods or Monte Carlo methods are widely used. But usually you're implementing them on a deterministic computer, like your laptop. And there, what you do is, you don't quite have a random number generator, you have what you call a pseudo-random number generator. So if you use MATLAB or Python or thing, you'd have access to these pseudo-random number generators, which you could use for this purpose. And what we have argued is that if you had a naturally stochastic random number generator, and I'll give you an example of that we had been working on, then you see you could have a fast, compact, and energy efficient building block. So in deterministic calculations, of course, random number generators is kind of one of those things you occasionally need. So you might have a specialized one there, elaborate one. But for probabilistic computing, it's kind of like the basic building block. You need lots of them. And so it is nice to have a natural unit that would be fast and compact and energy efficient. And this is kind of what got us into this area. So in the sense that my own background, like most of you, is in spintronics and devices. And what we were looking at was this use of this device called a magnetic tunnel junction. And in this series, I'm sure you have heard a lot of talks on this device. In fact, Shubhankar was just telling me that the last seminar was by Professor Ono, who is one of the world's experts on this magnetic tunnel junction. And there the idea is that you have these magnetic layers, that's these blue layers. And if the two magnets are parallel, then the resistance is low, that's Rp. And if the two magnets are anti-parallel, then the resistance is high. And you can store information. So you have a fixed layer and you have a free layer, and you can store information. And then you can sense whether it's 0 or 1 by measuring the resistance. So that's what is used as a memory element in this MRAM technology that I had mentioned. And what we had proposed was that, well, if you took one of the bad MTJs, meaning the one where this magnet is not stable, then what would happen is that the resistance would fluctuate. It would be sometimes Rp and sometimes RAP. And you could use that as a p-bit, as essentially this random number, a controlled random number generator, by putting it in series with a transistor. So this resistance is fluctuating. And so you have a fluctuating voltage here. And you can control, what this transistor allows you to do is to control how often you have zeros and how often you have ones. Because if the transistor is a low resistance, it would be you have one kind of probability. If the transistor is, transistor is a device whose resistance you can control with an input voltage. And so by changing this input voltage, you can change the probability of a 0 or 1 at this point. And then there's an inverter which turns it into a 0-1 signal. Okay. Now, so this is where, I guess, a couple of years back, we had collaborated with Professor Ono's group, and they're experts on MRAM technology. So they usually build stable magnets, but to help us, they kind of modified their process. You see, they're experts at this, and they kind of modified their process to deliberately build an unstable magnet. So they had to make the free layer a little thicker than normal. I mean, just one or two atomic layers thicker. And that made it unstable. See? And that's how we got these unstable magnets. And then they shipped it back to us just by express mail. And we took that and put it in series with this transistor and this inverter. And that's how we kind of demonstrated this p-bit and a p-computer. So what we did was took a bunch of these p-bits and connected it up to implement a optimization algorithm, an algorithm that actually we had borrowed from the quantum computing literature. So, but what we are doing was implementing it with p-bits. Okay. And that's described in this paper. And this Professor Ono is a co-author on this. And I understand he talked a little bit about what we had done there. I won't go into too much detail, but I just wanted to give you an idea of how Spintronics connects to this world of this concept of p-bits that I'm talking about, in the sense that it gives you a nice compact way of implementing a p-bit. Now, so what we've shown was this, that ordinarily, with some value of this input voltage, this transistor has a certain resistance. And so when you look at this point, the output voltage, it goes between 0 and 1. So half the time it's 0, half the time it's 1. Now, if you put a smaller voltage, then what happens is this resistance becomes high. The transistor goes nearer to its off state. And once it's high, this voltage tends to stay high more often. And so the output voltage is 0 more often and 1 less often. Similarly, if you go the other way, so you make this for V input high, then this is a low resistance. And then this point is 0 more often. And so after the inverter, it is 1 more often. So that's the point, that you can use this input voltage, which is an analog number, to control the probabilities of zeros and ones. So that's the basic thing that we had demonstrated. Now, so this is the actual time sequence of the signals. But if you looked at the average values, then you'd see this sigmoidal function. That if Vn is high, it's 1 more often. If Vn is low, it's 0 more often, etc. So these would be like the mean values as you change Vn. So this is the function that we demonstrated, and the point is you could implement it with regular CMOS technology, not bringing in any MTJs. You could make these pseudo-random number generators, and we have done that. So for many of the things I'll be talking about a little later, we have actually just implemented it with normal CMOS transistors. But the point is that in order to do it with CMOS, you need like thousands of transistors. Again, depending on the quality of the random number you want. These are pseudo-random numbers. So depending on the quality, you need like the precise number of transistors you need would depend on what quality you want. But the point is, generally, it's like thousands. By contrast, this device is just like 3 transistors, 1 here and the 2 for the inverter. And then you have this stochastic MTJ, the magnetic tunnel junction that we deliberately made into a bad MTJ, one that would be bad for memory. But in this context, point is that this combination essentially gives you that function. So what could you do with it? Well, this is where you could take these p bits and construct a p circuit. And p circuit is something like this, that you have a whole bunch of these random number generators, say n of them. You generate something, and then you have what we call a kernel, something that takes that, does certain calculations, and then feeds back that information to the random number generator so as to control the probabilities. So in other words, so left to itself, this RNG would be generating things with say 50-50 probabilities. But after the calculation, it might look at what you get and accordingly change things a little bit. So general structure of a P circuit would be something like this. You have random number generators, you do certain calculations, feed it back, etc. And then you eventually get an output. Now, what is this kernel? What kind of computation would you do? Well, that depends on what you want to use this for. Different applications would require different kernels. Now, one application that we actually showed in that paper was was an optimization problem. So usually what happens is that optimization problems typically have a cost function, that you have some quantity that you are trying to minimize. And that naturally maps into statistical physics, because as you know, in statistical physics, there's this Boltzmann law, which says that when you have all these different possibilities, each one has a probability that's proportional to exponential of minus E. I mean, normalized E, usually it's normalized to the thermal energy, E over KT. So what you can do is, given an energy E, so for a particular problem, if you're given a cost function, you could call that the energy function, and then design the kernel so that it works, so that all these different possibilities you get with probability, this given by a Boltzmann type law. And this class of machines in this literature, they call it a Boltzmann machine. You see, of course, Boltzmann law was came from statistical physics, where you are trying to discuss natural phenomena. Whereas here, what you're trying to do is, given a problem, trying to design a machine that will naturally give you the probabilities, naturally give you the answer, because the answer you're looking for is the one with the lowest cost function, which means the lowest energy, and the lowest energy has the highest probability. So one example that we showed in this paper was let's say I want to factorize a number, f, into x and y. So ideally, f should be equal to xy. So what I can do is I can define the cost function as f minus xy squared. So the idea is if xy is equal to f, the cost function is a minimum. It's 0. Anything else, the cost function is positive. It's bigger. Okay? And so this would then be what the energy function. And then what, I won't go into the details of this. I guess that paper I mentioned that describes how we did this particular problem. But the point is, given this energy, you can design your kernel so that finally the random numbers you get have the probabilities exponential minus e. So what we did was we said, okay, let's say you have 5 of these p bits. Each one can go back and forth between 0 and 1, and which we use to represent x. That means x then could be any number between 0 and 31. Because if you have 5 p bits, that's like 2 to the power 5 is 32. So there are 32 possibilities here. And similarly, y, you use another 5 p bits to represent that. So then you have these two numbers, each one of which can go up to 32. And with these 10, you get all these 1,000 possibilities, 32 times 32 possibilities. And then you design the kernel so that each one you finally get with certain will have a probability proportional to exponential of minus e. So the idea is, in this case, for example, if you ran it, you'll get all these possibilities, 32 x's and 32 y's, but they will have different probabilities. And the highest probability would be for the number, for the correct factors. Like in this case, I was just showing the example where the number f is 437, which is 19 times 23. So you'd get 2 peaks at 19 times 23 and 23 times 19. And there would be other lower peaks, the ones which are not exactly 437, but close to it. And all other combinations which are very far from 437, they will have a high energy and hence a low probability. So that's basically how you could use these Boltzmann machines to do optimization problems. Of course, the key detail I'm not going into is that given the energy E, how you design the kernel. But that's a well-defined thing, well known in this field. And for this problem, it's described in the paper that I mentioned earlier. By the way, you can hear me clearly, everything's fine? I mean, I don't see anyone, etc. So just want to make sure.
Everything is perfect.
Perfect. Okay, very good. Thank you. Okay, so there have been all kinds of other optimization problems that we have been looking at. And optimization problems are all very similar in the sense that finally there is an energy function that you are trying to minimize. And then you use this principle of Boltzmann machines to generate your kernel. So one problem been looking at is this protein folding problem. So you have a protein and the actual structure is determined by the one that minimizes energy. And if you have an energy function, which people have studied and figured out, then from that energy function, you could try to figure out exactly how it folds. So this is one example that we had done. And you can see that the one that we get from this optimization, it matches well the correct one. And I guess you start from this linear chain and then let it fold. I mean, try out all kinds of different combinations to looking for the lowest energy solution. Again, I won't go into details here, but the main idea I'm trying to give you is that this optimization problems appear everywhere, and they can all be addressed with this general Boltzmann machine principle. Another interesting example is this idea of invertible logic. You see, logic gates you're probably familiar with. That's everywhere in digital circuits. Like an AND gate is a very common thing where if the inputs are 0, 0, 0, 1 or 1, 0, then the output is 0. But if both are 1, then the output is 1. And usually there's a well-defined way of how you design these gates, but you could use this Boltzmann machine principle to design an AND gate. Because what you could do is, you see, there are these 3 bits, A, B, and C. Each one can be 0 or 1. So there are 8 possibilities. And you could design it so that the 4 possibilities that belong to the truth table have a relatively low energy and so a high probability. So then if you have this 3-bit P bits with the right kind of kernel, then what you'll find is the outputs will always belong to the truth table. So 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. These 4 will have high probabilities and everything else will be suppressed. Now, you could use this to, in the usual way you'd use a AND gate, namely, you can say, okay, I'll make A and B 0, 0 by putting a special bias on them so that A is locked to 0 and B is also locked to 0, so that they're 0, 0. In which case, only this peak will be seen and the C will also be 0. So that would be running the gate in the normal way. But the interesting thing about doing this in this way is you can also run it backwards. It is invertible logic. I mean, normal digital gates, you're supposed to give A, B, and then get C. There's no way you could turn it around and give it C and get back A and B. But in this method, you could do that. You see, if you lock the C to 0, for example, then what will happen is the Boltzmann machine will go back and forth between these 3 possibilities. And so you could look at the 3 combinations of A and B, which will give you an output of 0. So that's what we call invertible logic. And this idea has been exploited in many contexts to do all kinds of interesting problems. Like there's something called this Boolean satisfiability problem, and or SAT problems. And another interesting example is this factorization as an inverse multiplication. In other words, you set up a multiplier that multiplies 19 and 23 and gives 437. But then if you fix the 437, then it will give you back the factors. So Professor Kamsari, who used to be at Purdue, but now he's at UC Santa Barbara, recently wrote this paper, actually. You might find that interesting. It's on ConMat, which talks about these 2 types of problems. Now, one question that comes up in this context is...
Can I ask a question?
Yes, please.
Yes, sorry about that. Maybe you said that I missed it. You mentioned somewhere the factorization algorithm, the optimization algorithm. Is there a comparison as regards how much time and space in bits it requires as compared to a quantum computer, say?
Okay, I'll come to that. Yes, we have done a lot of comparisons and things depend on the specific problems involved, but I'll come to that a little later. And at the end of the talk, if you like, we can talk more about it also offline. But yes, again, depending on the algorithms and the problem involved, because the important thing about Shor's algorithm, for example, is that it is supposed to scale very well, that when you go to huge numbers, instead of exponential, it will scale more linearly. But then Shor's algorithm is very difficult to actually implement at this time. And you have to, and there's a lot of this quantum noise in noise problems, which one has to deal with. So there again, if you compare specific problems, I'd say, the probabilistic computers would compare well to what can be current, to what you could do with including the noise levels. Right? So we can come back to this. So, the answers are nuanced, depends on, but I'll try to compare quantum computing to probabilistic computing as we go on. Okay. Is that all right? Is that...
Yeah, please continue. I also request everyone to write the questions or wait till the end of the lecture. Let's finish the lecture first and then we will have the interactions. Okay. Please continue, sir.
Okay, so as I was saying, one of the questions that comes up is this idea of that, well, how fast can these magnetic tunnel junctions fluctuate? Because that's important, because what you're trying to do is get a very fast random number generator. And the examples we had used from these magnets from Professor Ono's group, those at a time constant that was more like 100 microseconds. And the question is, could you do it at gigahertz speeds? And that's where I guess one of the things we had predicted, this work in collaboration with Professor Sun and Professor Upadhyay, that we said that if you design it properly, you could actually get sub-nanosecond fluctuations. And this has now been demonstrated experimentally by two groups. One is Professor Sun's group at IBM. So this happened this year, 2021. And you can look up these papers. So there's these two groups which have now shown this sub-nanosecond fluctuations. And one group is from Professor Ono's group, I guess Tohoku, and this IBM group, Dr. Sun's group. Now, so what we have been trying to do then, last couple of years, and this will, I guess, connect to the questions that Professor Benjamin was asking, is what we have been trying to figure out is what kind of problems could you do with these p-bits? And of course, it would be great to use the stochastic MTJs, but that will take some time before you get to the point where you can build P computers with thousands of these stochastic MTJs. So instead, what we have been doing is using CMOS technology, using what is called this field programmable gate arrays, which emulate the stochastic MTJ. So they kind of mimic it. And so it gives you an idea of how a system might operate using today's technology. So you can explore all these different algorithms, like we have implemented Shor's algorithm, for example, using these FPGAs. And that way you can get an idea of what one can expect. Now, of course, the distinction is that when you use FPGA, because you need thousands of transistors for each random number, you can only get, say, 10,000 of them on a reasonable size system. And whereas if you use stochastic MTJs, then each one would involve just 3 transistors. It would be much more compact. So you could get millions of them. So when you look at how many random numbers per second you can get, what with FPGA, with the CMOS technology, we get about 10 to the 12th of them. Whereas we project that with MTJs, you would have got like 10 to the 15th. And so most algorithms would get speeded up by 3 orders of magnitude if you could actually do this. And we have been using this argument trying to motivate people to actually do this, use stochastic MTJs to build these systems. But what I'll be doing for the rest of the talk is giving you some examples using this CMOS technology. See, so what we have done is this is on Amazon Web Services where you can rent these FPGAs. So it's a 125 megahertz FPGA, which we use, and you can go to this website. Anyone could actually use it. So, and with this, we have demonstrated these P computers with like about 10,000 P bits, right? And this is all described in this paper. Now, what kind of examples have we shown? Well, there we showed examples of what you might call these Boltzmann machines that I talked about before. One of them is this max cut problem. And the other problem is quantum annealing, which is based on this transverse field Ising model, using what's called the Suzuki-Trotter transformation. But these are all described here, and it shows how P computers can speed it up enormously, the application of these things. But one point I want to mention is, although I've talked mainly about Boltzmann machines, there's actually a much wider class of problems, what we call this Monte Carlo methods, which could use a P computer. So Boltzmann machine is kind of a subset of this whole general field. I mean, Monte Carlo has been called one of the top 10 algorithms of the 20th century. And as I said, normally you implement them on deterministic computers, but with a P computer, you could speed them up enormously. So in general, what we have shown for a wide variety of problems is something like this. You take a particular stochastic algorithm, implement it on a CPU. Then you have this time to solution versus the number of samples you take. And this red curve is the CPU curve. If you have GPU, it has a certain amount of parallelism. So you usually get you can get more samples at less. For a fixed time, you get more samples with GPU. But then GPUs cost more than CPU. So if you do this comparison ISO cost, then this gray line would be the curve, and that will be comparable to GPU. But what we are doing with these emulated P computers, that gives you a lot more samples for the same time, because it's although we are using this 125 megahertz FPGA, not a gigahertz one either. And what we project is that if you actually did this with compact things like MTJs, you could be even better. So that's this general thing we are saying, that all Monte Carlo algorithms could be speeded up enormously with using this principle. Now, one example I often give here is a very good example of what I feel probabilistic computers could be useful for. And that is this. And this is just an example. There are many problems in this category. And this is what I call the genetic correlation. That supposing we want to find the correlation in the genetic correlation between different generations. So there's parents who pass on the information to the child, goes on to the grandchild, and so on. So if you look at the correlation between a parent and a child, it will be about 50%. And what is well known is every generation, it would go down by a factor of 2. Now, how do you calculate this? Well, that's where if you set up a P computer, it would give you a natural way of doing it. What you do is you'd have all these P bits, each one is fluctuating. And then let's say I want to know the correlation between the parent and the grandchild. Each one is a time varying signal. You look at you run it through a XNOR gate. XNOR gate in the sense that if both are 0, you get an output of 1. Both are 1, you get an output of 1. 1 is 0, 1 is 1, then the output is 0. So this way, you calculate the correlation, how often the parent and the grandchild have the same unit. Now, this is the thing that, Feynman's 1982 paper, which is generally motivated all this work on quantum computing. Before he goes to quantum computing, he talks about a probabilistic computer. And he tries to make the point that, you see, if you try to calculate this probability analytically, then you would have to calculate this entire huge probability function and then integrate it out all the marginal variables, all the other ones. Whereas if you had a probabilistic computer, then all you do is look at the nodes you're interested in and look at their correlation. So this is a point he had made very clearly in this famous paper, where, as I said, the paper is about quantum computing, but before he goes to a quantum computer, he talks about a probabilistic computer very clearly. Now, and this is something, so I'm showing this example that how you could calculate this genetic correlation. So what you're here on the x-axis, what you have is the number of samples, y-axis is the correlation. And of course, if you look at the correlation between a node with itself, then it's 100%. If you look at the correlation between a parent and a child, it's 50%. Parent and a grandchild is 25%. Then parent and like 3 generations later would be 12.5%, etc. And what I'm showing is you can get these correlations very accurately. And if you're totally uncorrelated, then it's 0. But the way you'd go to 0 is that as you take more and more samples, it would basically approach 0. It would go down as 1 over square root of ns. So this is the kind of thing, although I'm using a genetic correlation to drive home the point, but the thing is this kind of problem is everywhere. where one set of nodes affects another, which affects another, and you want to know the correlation between different nodes. Like medical diagnosis is a similar problem. And all of these, what I argue is, could benefit from a P computer, because what we have shown is that all these classes of problems, if you implement it on a CPU, you'll get, this is the curve. If you do this on an emulated P computer, this is the curve, and this is for a projected P computer, and you could get much faster. So for the same time, you could collect many, many more samples here. That's the point. Now, let me just try to, finish up. And this is where I want to make a little connection with the quantum computing. And that's, a question had come up on that. And as I mentioned earlier, that there's a lot of mathematical similarity between probabilistic and quantum, in the sense both operate in this 2 to the power n space, actually. But the difference is, of course, this is positive and this is complex. And one of the comments that actually had intrigued me in this Feynman's 1982 paper, he made this comment: the only difference between a probabilistic classical world and the quantum world is that somehow or other it appears as if the probabilities would have to go negative. Now, he said negative, but I guess more generally it's complex. And of course, that's what allows you this interference. And good quantum algorithms try to make use of that interference phenomenon. But in either case, of course, as I said, the real power comes from operating in the n space, but actually dealing with this 2 to the power n information in this 2 to the power n space. And now, the sampling method that I described, although it's widely used for classical things, the point is they can be used for quantum problems as well. That's this vast field of quantum Monte Carlo. But there is a problem, and that's what I want to explain a little bit. And this point you can understand if you just look at a simple problem, quantum computing problem, which is just 2 states. Just one qubit has 2 states. You have something called the Hadamard gate. What that does is, and the matrix for a Hadamard gate, you'll notice, has a -1 in it. And that's, of course, what makes it non-classical, because classically, everything should have been a positive number. So it takes a 1, 0, turns it into 1, 1. But because of that minus, you have this interesting possibility that when you operate it again, you can actually go back to the original state. And there's a very nice way of visualizing this in terms of what are called Feynman paths. When you multiply matrices, which is basically in a way a pictorial representation of matrix math. So when you multiply it, so you start from 0, that's this state. And in the end, you can go to a 0 state through 2 paths. And represents this matrix multiplication. And they add up so that you have a high probability of being here. On the other hand, you also have 2 paths going to the other probability, but there they cancel out. And that cancellation, of course, is made possible because of this -1. So the point is that you have 2 paths going to one output, 2 paths going to the other, but in one case they cancel and in the other case they add. And quantum computing tries to make use of this cancellation, which never happens with classical systems. Now, supposing you have a large number of gates, like D gates here. So then there's lots of paths. You see, there are like at each state, there's 2 to the power n possibilities and raised to the power d. So that's an enormous number of paths if you have n qubits and d gates. And what a sampling technique would do is it would sum a fraction of those Feynman paths. Now, but you could use that even if the paths have complex weights. You could use sampling to sum this fraction. But what would happen though is something like this, that supposing you had 10 such gates, and so 2 to the power d was 1024. And at the end, the paths leading to 0 give you a peak, and the paths leading to 1 give you a null. But the point is, in this case, what happens is of all the possible paths, they just cancel out. Half are plus and half are minus. But in the other case, where you get a peak, it's not as if they're all positive. But there's a cancellation. There's a more of plus than minus. And that's why you get a peak there. So after taking 500 samples in this case, you get a net signal of only 30 or so, because there's this cancellation involved. And this is where, of course, if you had done it with qubits, then what would have happened is, if you had taken 32 samples, they would all go to 0, because it would kind of instinctively know that that's where it should go, because it's not really using cancellation, kind of doing that enormous addition of all paths instinctively and giving you that. And that's why, you see, the quantum computer can be much more efficient than a probabilistic computer. This probabilistic computer, you have to take 512 samples to get a signal of 32. The quantum computer, just 32 samples would have given you that. And here I'm using a number to illustrate the point, but as D and N go up, that difference becomes enormous. But the point to notice that this also requires, though, that you have a very delicate control of phase, that all these paths cancel perfectly. And the real problem with actual computers, quantum computers today, is that one has to live with a lot of noise, which is why nowadays people focus on what they call this noisy intermediate scale quantum computing, or NISQ computing. The idea is, despite the noise, how well can you do really, right? So this is the thing, that with probabilistic computers, of course, you have to deal with this sign problem. But with quantum computers, you have to deal with this noise, this delicate control of phase, which requires, of course, you to go to very low temperatures, etc. Now, we have looked at many quantum computing problems, actually, using quantum Monte Carlo. This includes both what you call gated quantum computing, like Shor's algorithm, and also adiabatic quantum computing, which is based on more the statistical mechanics principles. And the difference is that in gated quantum computing, you're always have these interference and cancellations. So you have what you call the sign problem. Whereas with adiabatic quantum computing, there are certain problems where where there are canceling paths. But there are also many problems where they're all positive. In that sense, they're very classical-like. And the technical word for that is stochastic. You can Google that word, you'll see the literature on this. And so stochastic problems don't quite have a sign problem, where there are also non-stochastic ones where they have this. So the main point I'm trying to make here is that there is this, in quantum computing, the problems one addresses, if you address it with qubits, then you have to deal with the noise problem. Whereas if you address it with p bits, then you have to address this sign problem. And depending on the problem at hand and the algorithm at hand, one might work better than the other. But this is really an open question. And in general, people are now trying out all kinds of algorithms and trying to see how far they can get classically with, say, probabilistic methods or otherwise, compared to the quantum one. But that, in my mind, is an open question. But what I've been trying to stress, and I hope I managed to convey this, is that, you see, when you look at deterministic and quantum, they look like worlds apart. And people talk about how in the quantum world, you have this enormous parallelism, 2 to the power n paths, etc. But probabilistic kind of introduces some of those features in an interesting way. And so it gives you a kind of a bridge, a mental bridge from the familiar deterministic world to the quantum world. And in fact, as I said, Feynman's paper did just that. When talking about quantum computing, he started with probabilistic computing and then went on to quantum. But at the same time, of course, the point I want to stress is that probabilistic computers also have a lot of use for problems that are non-quantum, that have nothing to do with quantum. Because, as I said, Monte Carlo algorithms are everywhere. It's like, as I said, the one of the top 10 algorithms of the 20th century, and they could all use a probabilistic computer to speed up. And that includes many practical problems. But conceptually, though, what I find most interesting is this notion of this probabilistic, the p bits, as a bridge from the deterministic world to the quantum world. As you know, one of the very fundamental questions of physics we always wonder is how the quantum world becomes our familiar deterministic world. And I think this probabilistic world is a nice intermediate step that kind of throws some light on how this quantum world becomes deterministic. And the one question that has always intrigued me, this Feynman's comment that the only difference between the quantum world and the probabilistic world is that in the quantum world, it's as if the probabilities can be complex. Thank you. Let me stop and you can.
Yeah, thank you so much, Professor Datta, for this wonderful overview. I think we have a very large audience, more than 110 people today. It was really nice. Thank you for taking us to this world of probabilistic computing. Before we take questions, I request you to stop sharing your screen, and I request everyone to switch on your camera so that we can take a screenshot of group photo. So please, yeah, thank you. Okay, Tamalika is there, very nice. I see many known faces. All right, Wolfgang is there, but your camera is not on. Maybe. Okay, I take some screenshots now. Second screenshot, we have a lot of people. So many people have not turned on the camera, but I respect their privacy. But I just still take photos. Okay. All right, thank you so much. So we can now turn up the cameras and we can now take questions. So I request Professor Datta to again share your screen because maybe some questions related to some slides.
I see some things on the chat box.
Yes. So should I read it?
Okay, I guess we could go through it one by one.
All right. So first question by Sachiraj Mishra. What does it mean by stable and unstable magnet? I mean, physically, there are different kinds of magnet, such as diamagnet, paramagnet, ferromagnet, but this kind of magnets I have not heard previously.
Okay. Yes. So I guess what we are talking about is ferromagnet. So if you look at a regular magnet, then it is usually pointing in one direction and stays that way. But of course, it could point in the opposite direction also, and that would have the same energy. So you might think that it would be, those are both equally likely, but usually in a big magnet, what happens is if it is in one of those states, it will stay there forever. I mean, forever meaning for millions of years, because there is a huge barrier to getting flipped over. But when you go to nanomagnets, then you could have a situation where you have two stable states, but then the barrier that is separating them is not thousands of KT, but only say 10 KT. In that case, the magnet will be flipping back and forth between the two possibilities at a relatively high rate. And that rate could be minutes, could be milliseconds, microseconds. And what we have argued is if you have properly designed it, you could even get them to flip back and forth at a nanosecond rate. Right? And now that's experimentally shown that you could have these nanosecond fluctuations. Right? So let me go back to the sharing. So I guess that's what is showing in that, yeah. In these two papers, this is from 2021, where they showed how so when I said unstable magnets, meaning that magnet has two stable states, and unstable means it just can't make up its mind. It keeps going back and forth between them. So basically a ferromagnet, but goes back and forth.
Yeah, I guess maybe it's a student, if I'm allowed, it's like if you have left-right magnetic orientations, and it is like a double potential well, and it can just fluctuate between these two states just because of the thermal energy or any other excitation. So.
Right. That double potential well, I think, yeah, I wish I had that picture somewhere.
Yes.
That would have simplified it very well.
Yes. But Professor Datta, you can kindly share your screen because we are going to take some questions. Maybe something related to the slides. Okay, the next question by Indranil. Why making thicker free layer leads to magnetic instability?
Right. So very good question. Right. So what happens is with magnets, with these nanomagnets, if it is thin, then it wants to be perpendicular. That's what they call PMA, meaning you have a thin film, and if it is sufficiently thin, then the stable state is the one where it is perpendicular to the plane of the magnet, the magnetization. Whereas if you make it thick, then it wants to be in plane. So if you have just the right thickness, then you see it becomes unstable. It doesn't quite know which one it wants to be. And so usually what happens is they make it very thin so that the stable state is the perpendicular state. And it either is pointing upwards or downwards relative to the plane of the magnet. But if you have just the right critical thickness, then it is able to go back and forth very quickly. And this is where, of course, Professor Ono's group, they're very good at it, and they have very good control over the technology. So they just added 1 or 2 atomic layers to it, and that made all the difference.
Yeah, so I mean, you just mentioned about this. It's just around the spin reorientation transition, where it clips from perpendicular to the in plane. And yeah, Professor Ono's group and other groups have shown very nice work on that. The next question by Amit Basu. How to choose X and Y? Classical program needs to go up to n by 2 here, also the same limit that we need to go up to.
Yeah, I'm not sure I got the question.
Yeah, I'm also, Amit Basu, are you there? If maybe he's not there. So this question is a little bit,
so I was wondering, is he talking about this X and Y? Or?
Maybe, I don't know. Okay, I think we can go to the next question by Soumya Dasgupta. Quantum computing is promising, but it hasn't been used for solving problems because of errors or decoherence. The P bit is based on fluctuations, so won't there be any problem due to such fluctuations? Or is it possible to control these fluctuations?
Yes, yeah. So because the way I think usually is that they are very similar, this quantum and probability, probabilistic. In one case, you have these complex things, and the other case, you have these positive things. But otherwise, in quantum computing, people talk of entanglement. The corresponding thing with probability is correlations. So what you're really controlling is the correlations. So for example, this application that I was mentioning, the one where we factorized these numbers. So the factorization, for example, so there are these 10 bits which are fluctuating. So there are 1024 possibilities, but only certain combinations have a high probability. So that's what you call a correlated state. Right? Correlations meaning it's only the correct combinations that will give you the best, that will have a high probability. And so this correlation is kind of the classical equivalent of, I guess, entanglement, right?
Okay, thank you. And the next question by Mihai. I think you can unmute and ask, please.
Hello, can you hear me?
Yes.
Yes, thank you very much for your presentation, and I feel very lucky to be able to attend. And I've been recently becoming interested in this subject of probabilistic bits, and I was wondering about, you have mentioned before about the switching rate of these low barrier nanomagnets. And I was wondering how the switching rate can influence the time to solution, I believe that's the term you used before, because I think I've heard that a faster switching rate in the terahertz range would help to improve obtaining the solution. And yes, that's my question.
Right. No, yeah, very good question. So because the point I was making in a lot of these Monte Carlo algorithms is that you need to generate random numbers very fast. Because what you're trying to do is, in Monte Carlo algorithms, how good your solution is depends on how many samples you took, right? Because with sample, like with
just as you've shown
samples,
on the graph before, indeed.
Right,
indeed.
right.
Yeah, yeah.
The more the samples, the better it is, right? It is basically trying to predict an election from exit polls, right? And if you have done it right,
I can see that, yes.
Right? Okay. So the important thing is how fast you can collect these samples. So question is, how fast can you generate your random numbers? So with magnetic tunnel junctions, what we have said is, okay, we can maybe integrate 1 million of them together. And each one could be fluctuating at 1 nanosecond. And this is what till 2020, there wasn't very good evidence that you could be 1 nanosecond, because the experiment we had done was more like 100 microseconds. But now I think there is experimental evidence more and more that it can actually happen in sub-nanosecond speeds, or at least 1 nanosecond. So 1 million flips, 1 every nanosecond, that gives you 10 to the power 15 flips per second. And flips meaning random number generators.
Indeed,
so in that
indeed.
sense, if you do it right, you could be collecting 10 to the 15 samples every second.
Yes, that clearly answers my question. Thank you. Could I maybe ask a follow-up question? If I'm...
Yeah, please.
Thank you so much. So I'm used in normal CMOS computing of clocked computers, right? That work on a certain rate. And it's difficult for me to imagine this concept applied to a probabilistic computer, for example, because I imagine that this adjustment of the probabilities happens continuously in a sense. And maybe you can help me understand better this.
See, yeah, I guess, yeah, when we implement this on a FPGA, FPGA is this field programmable gate array, where it is based on standard CMOS technology. So when we do this, we are using the standard CMOS technology that's available through Amazon Web Services, actually. And there we have these pseudo random number generators, and we have 10,000 of them. And the 8 nanosecond here, that number comes from the clock speed, actually. So what we have from Amazon Web Services is this 125 megahertz FPGA. So 125 megahertz is what corresponds to this 8 nanoseconds, because inverse of 125 megahertz is 8 nanoseconds. So it is all being run in a clocked way. So it's like I generate a random number, do some calculations on it, and depending on what I get, I generate the next one. But when I do the next one, the probabilities get adjusted. So I generate a random number every clock cycle. But the first time, maybe I was generating 0 and 1 with 50-50 probability. But the next time I might do it with 30-70 probability because I got some feedback, etc. In that sense, it's generating random numbers on the clock, but with probability that is getting adjusted.
I see. Okay, That is
what I've been doing. But in general, with this probabilistic computers, you're right that we have been exploring two types of architectures, I'd say. One where it runs synchronously, meaning with clocks, and the other where you just let it run asynchronously. So I think this paper here that I referred to, the one in IEEE Access, that one described an asynchronous way of doing it. Whereas recently we wrote a paper which was all largely synchronous with FPGA. So you could do both actually.
Thank you very much. Thank you.
Yeah, thank you. On a lighter note, Mihai, may I know from where you are actually joining?
Yes, I'm from Groningen, from Professor Banerjee's group.
Oh, okay, okay, very nice. All right, this next question. Before that, I have actually one very curiosity question. The quantum computers, what we are talking about, like from superconductors or other materials where we have to really go to cryogenic temperatures. But the probabilistic computing, what we are talking here, actually these are all at room temperature, isn't it?
Yes, yes.
Yes.
This is all room temperature.
Yeah. Okay, thanks. The next question by Sriram in the chat box. Can you please comment on material features, like what kind of ferromagnet gives this unstable nature and what are the specific parameters to control its growth?
Okay, so this is where I guess the actual experiment that we did, that was based on what we had got from Professor Ono. So you can look at that paper, the one I referred to. I'm trying to, it was.
And the PRL paper.
No, this was actually in Nature.
Okay.
Yeah,
okay.
This was appeared about 2 years ago in Nature, and this one used these stochastic magnetic tunnel junctions that we got from Tohoku, that is from Professor Ono's group. And they are, of course, experts on MRAM technology, and normally they build stable magnets, but they kind of use their expertise to help us by making unstable ones and sent it back to us. So that's what we had used. So the details of the magnet you can find in that paper. So that's the only experiments we have done with real actual magnets. Everything else we are talking about here is just emulated things on with CMOS technology. Okay. But I'd say this paper gives the detail of the only one that we have done with real magnets. And there's a lot of other work also, you know, on magnets in general in this field, right? In terms of making random number generators with magnets. But I think this paper should have the references.
Okay. Next question by Sandeep Kapila. You may unmute and ask your question.
Yeah, I think my question is on similar lines in terms of what's the status of the hardware side of building qubit computers, like actual physical computers. I think one part was answered that it's at room temperature, but just what technologies are being used and how many qubit computers have been made till now, or where is that headed, the hardware side?
Yeah, thank you. So I'd say that using this magnetic tunnel junctions, the only thing we have done, only thing that has been done, I think, is this 8-bit computer that's described in this paper. But what we have been doing lately, and half my talk was about that, is where we have emulated it with CMOS technology. So it has the same architecture as a probabilistic computer, but the random number generator is a pseudo-random number generator, actually. And there we have, I mean, this paper describes a computer with, I guess, 8,000 qubits. And we also have examples where we have almost about 10 times that also. So we have an example where we had about 80,000 qubits also. But these are being done with just normal CMOS technology to emulate a random number generator. Does that make sense?
Yeah, but I think the part of FPGA was clear, so it's also clear hardware-wise that it's still at 8 qubit, and that's where I guess the potential is also, right, for more work as well.
Right. And I know people who are looking at different hardware possibilities, because the whole idea is that when we use FPGA, you're taking thousands of transistors to build a random number generator.
Yeah.
But if you can do it with much less transistors, that's the advantage, really. So I know people who have been trying to do it with using Zener diodes or other things also.
Okay. Yeah, that's what I was like. What are the hardware technologies to look at? So Zener diodes is one.
Yeah, I don't know whether that is a published thing, but I know that there are people who have been trying other things. Yes. Yeah, I couldn't immediately give you a reference for that one.
Okay, we need to stay tuned for the developments. I take the next question by Sen Uno. Can you please comment on the Monte Carlo algorithms that can run on P computer? In which direction we can design effective algorithm based on P bits?
Yeah, I guess generally speaking, I'd make a distinction between this pure Monte Carlo and what is called Markov chain Monte Carlo. So pure Monte Carlo would be kind of feed forward. That is, you have random number generator, you take the random number, operate on it with a kernel and move on. So you don't need this blue arrow back. Whereas Markov chain Monte Carlo means that when I generate the next random number, I look at what I currently have and use that information to intelligently generate the next one. So if you want Markov chain Monte Carlo, then you need this feedback, this blue arrow, the one that feeds back. But in either case, I think having fast RNGs could be very useful, right? And that is where we have looked at a fairly wide variety of problems, and I tried to give you an example of some of those. So one example was this genetic correlation problem that I was saying. So this is what I'd call feed forward. So here, you just generate random numbers, and based on the random numbers you generate for the parent, you then use it to generate the random numbers for the child, which you use for the grandchild, and so on. That's pure Monte Carlo. But then the optimization problems are all in the category of what I'd call Markov chain Monte Carlo. And I think, yeah, all of them could be speeded up using fast, compact random number generators.
Okay, thank you. I think we had a wonderful seminar. I like to present a small token of appreciation. So Professor Datta, if you may kindly stop sharing, I like to share my screen. And a small advertisement that next week we will have the seminar also at the same time by Professor Emily Jue from NIST in US. Now I like to share my screen and present a small token of appreciation from our W2S team. I hope you can see my screen.
Yes, thank you very much.
Okay, so on behalf of my co-convener, Dr. Brajbhushan Singh, my teammates Puspendra, Ajay, and others, from NICER, from the audience, so I take the greatest pleasure to present this small plaque, digital plaque. I read it for you. W2S seminar, webinar series on Spintronics, NICER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Supriyo Datta from Purdue University, in recognition and appreciation for being a valuable speaker to give a lecture on P bits between a bit and a qubit. So thank you so much, Professor Datta. On behalf of everyone, a large audience, more than 100, I'm really happy to have you today. And we hope we can meet in person soon. Maybe we will be able to welcome you one day in NICER physically, or see sometimes. So you may kindly also join our WTA seminars, and I look forward to see all of you. Until then, please stay safe, stay happy, and thank you so much all. And thank you so much again, Professor Datta, for your excellent overview of the lecture. Thank you.
Thank you very much.
Yes.
Thank you very much. It was a pleasure.
Bye-bye.